Hi, my name is Hala Lamdouar, and I will present our paper, The Making and Breaking of Camouflage, in collaboration with Wei Dishe and Andrew Zisserman from VGG, University of Oxford. In this work, we ask the question, what makes a camouflage effective? Consider the octopus in this example. You can see that it changes its patterns dynamically and rapidly as it moves from one spot to the other, constantly adapting and improving its camouflage. It's like a continuous search for optimal blending with the background. Understanding what makes such camouflage successful is an essential step towards robust video camouflage breaking. The contributions of our paper are the following. First, we investigate scoring functions that assess the effectiveness of camouflage and propose the first automated vision-based quantification of visual ambiguity in terms of camouflage challenge. Second, we introduce a scalable pipeline incorporating the camouflage score for synthetically generating challenging camouflage datasets with increased realism. And finally, we use this dataset to train a transformer-based model to robustly break camouflage in videos, achieving state-of-the-art performance on MocaMask. To formulate, our task is, given a pair of image and mask, to compute a score between 0 and 1, expressing how hard it is to spot the camouflaged animal indicated by the given mask. To assess the effectiveness of camouflage, we focus on the following key aspects. First, background matching, or how well the animal succeeds in reproducing visual patterns from its surrounding. Our reconstruction fidelity score addresses this aspect. Intuitively, if a camouflage is successful, we should be able to reconstruct the foreground animal perfectly by simply copying patches from its close neighborhood. This score measures the similarity between the original foreground and its reconstruction from the nearest patches of the background. The second aspect we consider is boundary visibility, or how well the animal blends with its background at the contours. For instance, are there any shadows or boundary effects that make the animal stand out? For this, we consider the boundary region highlighted in green in the tree map and compare the contours in the whole image C obtained using our off-the-shelf contour detection method to the animal's contours CGT. The animal would stand out if its contours are visible within the whole image contours. This is an example of dataset ranking showing top and lowest scored images using S-alpha, a linear combination of our two perceptual scores. We demonstrate that this score exhibits strong correlation with human-produced rankings. We also propose a probabilistic proxy inspired by the Fréchet-based metrics. We follow the hypothesis that the features of the foreground and background regions, produced by a neural network VV, follow a normal distribution and compute the Fréchet distance between those two distributions. This function has the advantage of being differentiable with respect to the VV's network's parameters, and so we can backpropagate through it in order to generate better camouflage examples. We first start by generating still camouflage image datasets. To this end, we considered an adversarial setting where the generator outputs a pair of image and mask, such as the discriminator cannot distinguish from real examples. We incorporate the differentiable Fréchet proxy for our camouflage scoring as an auxiliary loss term LF to further enforce camouflage effectiveness in the generated samples. We also added an extra fake sample of non-corresponding image and mask from the training set to further enforce the correspondence between the generated images and masks. We obtain realistic object masks with rich backgrounds, mimicking structures that we find in real examples. After adding the LF loss, it can be seen that the generated animals better blend with the backgrounds. The GAN model generates still images that we transform to sequences by applying different motions to the foreground and background, while including static subsequences to mimic the case where the animal remains still. We adopt a transformer-based motion segmentation architecture coupled with an appearance stream aggregated using a transformer decoder and train it on the synthetic dataset using the binary cross-entropy loss. Our experiments included all publicly available camouflage datasets for still images, and also video and multiple view datasets. Our results show that training the generator with the additional LF loss results in improving the effectiveness of camouflage according to all our proposed scores. Finally, we obtained state-of-the-art performance on video camouflage object segmentation by training on the generated effective camouflage sequences. Thank you very much for listening.